Is it already now recorded?
Yeah.
Okay. Let's get started. So, last time we had introduction, and then today we're going to the detail of transformation and so on. So, okay, so let's consider a transformation rule. Transformation rule. Okay, let's also transformation here. So if you act on translation, the del P of phi I usually just give you the prime mu phi I. So this is the translation you learn from the. And also, if you consider the rotation J of phi I is something like a x mu, partial mu, minus x mu. And J and I and phi J. So that's the usual way of doing that. So as I mentioned last time, so this is the generator of the rotation. But here is the extra thing depending on the spin of field phi J. Okay. So let's look at the example. Consider spin 1 here. So, for instance, spin 1 field is something like a gauge field with a point the spin 1 field, and then let's look at how it transforms. If you look at the upper indices like this way, then x prime is equal to partial x prime mu, partial x mu, and mu x. So that's what we learned from this usual transformation of the field. And then we know the rotation is generated by like this way, x mu plus 2 epsilon mu x mu. That's what we learned last time. So this epsilon tensor will give you a rotational generator. Okay, and then okay, then we just look at the transformation rule of this field. A prime rho of x minus a rho of x, and this one will give you given by. The first of all, so this is x prime, so you have to transform to x prime to x. So the x is equal to x prime minus 2 epsilon mu, like this way. Okay, so therefore you have to do a tail expansion. So therefore a prime of rho x minus 2 epsilon mu x mu partial mu rho, like this way. So this is the case. And then we have extra one. So this one, this contribution you need to take into account, which is plus 2 epsilon rho sigma and sigma. and then minus a. That's that. So the first one is just tail expansion. Just plug this one into here and then do the tail expansion. Sorry, maybe. Yeah, I think. Yeah, tail expansion, and then you get this one. And moreover, so if you have the since you have an extra transformation rule, so that will give you this back, and then difference. And eventually you get that minus 2 epsilon mu. But maybe I should write down like this, minus 2 epsilon mu. 2 epsilon sigma. Like this way, and if you massage this equation, what you get is the as follows. And then plus delta sigma mu A mu sigma minus delta rho mu A. Okay, so that's what you get by massaging this the upstairs. Okay. And by using the fact that the epsilon mu nu is a antisymmetric tensor. So epsilon mu nu is equal to minus epsilon mu mu. Okay. So this is the antisymmetric tensor. If you use this one, so this one is easily, you can see this factor 2 coming from this. If you just antisymmetry, you get this one. And if you just add antisymmetry this one, you get this one. Okay, so that's what you get. So now, if you compare between these two, for spin 1 field, this part, corresponding to this part up to some size. Okay, so therefore, we can conclude that the S mu vector or spin 1 or whatever vector of low sigma is equal to minus delta rho mu and mu sigma minus delta rho mu and mu sigma. Okay, so that's what you get from this analysis. So therefore, because of the so originally this part really coming from this part. It's coming from this part. So since the spin 1 field will transform non-trivially under the Fourier transformation, this will give you the extra piece for field. Likewise, similarly, if you go to spin 1 half and so on, you get the same phenomenon. Okay. Fine. Okay, let's move on. And we can do the same exercise. It's here we consider upper indices. The transformation is the upper indices here. But you can consider lower indices. So you have to be careful about this kind of stuff. And mu of x, and you have to do the same exercise. If you do the same exercise, you will get the delta and rho is equal to, I'm not going to repeat everything. Since here now we have a different, how to say? So x prime upstairs here, whereas the x prime is downstairs here. So you have some extra minus sign will involve a prime rho of x minus a rho of x, which is equal to 2 epsilon mu. This part is the same. but here is the extra minus sign. Okay. Fine. So therefore, this one is equal to epsilon and mu. Like this. So from before you get the extra plus sign involved. I'm sorry, I think I missed the overall bracket. So here's the overall bracket here. Sorry, the overall bracket here. I missed the overall bracket. So here it was used to be plus sign, but now it becomes negative. So you have to be careful about this kind of sign issue when you lower the indices and so on. Okay, so that's the case. Fine, and we can do the same exercise for, so this is a translation, and this is the rotation, or Lorentz symmetry, whichever is okay. I mean, it depends on, and it depends on if you want the Euclidean signature. And what else did we look at last time? As a symmetry of conformal transformation, generator of conformal transformation. On Wednesday, like 2 or 3 days ago. What else did we see? So translation, Lorentz transformation. Another is the scaling transformation, dilatation. Okay. Another thing is dilatation. People just have the formula, the x prime is equal to. Dilatation is essentially x prime goes to lambda x, and this transformation of lambda is transformed like this way. Phi x. And this delta of phi is called the scaling dimension, or conformal dimension, or many names. It has or weight. There are many names depending on the people. Okay, and then so under this transformation del phi is phi. Okay, so under this transformation, we will get the phi of I. Transformation is minus x mu partial mu of phi I plus delta phi. Okay. So that's the transformation rule we get from this one. So note that so if lambda is very small, so x prime is something you can just approximate like this way, and then look at the leading order of epsilon, and then you will get the x mu. You will get the this term. Okay. More precisely, you get the minus epsilon like this. And then do the expansion, and then you so this is a transformation rule for under the scaling transformation. Okay. And now we will consider the following thing. So we consider the following thing. How about the special conformal transformation? The question is special conformal transformation. So the last time we just the global transformation is something like you just put the x here and the inversion of the inversion, and it just do the translation, and then here x divided by x squared, and here x divided by x squared plus a, and the complex. Do the take another inversion. That is the x prime. So that is the global version of the special conformal transformation. And then, so this case is the, as we recall, so this one is somewhat related to the following fact. So the transformation, to see the transformation, we can use this fact. Yes. Plus 2j mu. Okay. So the last time I introduced the commutation relation or conformal algebra, and then the commutation relation between P and K are given in this form. And using this fact, one can easily see that here. So this means that the del P and del K minus del K del P, okay, times I should be equal to 2 times eta mu nu del D plus 2 times del J. Okay. So that's what you should get, you expect to get. And we already know that del D, and then del J, and del P. So therefore, using this commutation relation, even though this special conformal transformation is complicated, one can just obtain the last time, one can obtain the transformation rule. So del K is of phi is minus 2x mu like this. So what can I expect like this way? So as you can see, so this one is original K generator. Last time, so we already see this one is the generator K. Mu is this exactly I times this one, right? 2x mu. X mu, partial mu, times x squared down. So this is the generator of the special conformal transformation, as we saw last time. In addition to that, you need an extra piece, okay? Extra piece. And as you can easily see, if P acts on this one, so P is a derivative with respect to the coordinate here. So if del P acts on here, you get the 2 delta, right? 2 delta phi, which is the same, which can be obtained by this one. Okay. So this one, what was it? So this one can be understood as the S of the dilaton. Of the field here, field phi I. So in addition to in the Lorentz transformation, in addition to the ordinary transformation, you need extra pieces. So now similarly, S dilaton has extra pieces like here. So in the same manner, so the special component transformation requires that in addition to the ordinary pieces for field, we see extra pieces. And then to see this one, you can just look at the del P acts on. Here, you get the 2 times eta mu nu delta piece. And del P acts on this guy, you get the delta J. Delta J will give you this. Okay. S mu nu phi is exactly this one. This one. Okay. Exactly this one. Okay. That's a transformation rule one can get. Okay. Okay, so that's that. And if this transformation is satisfied, this phi, if this transformation is satisfied, so then phi j is coprimary. That's the primary field we will get. Then one way to define primary field. And if you act on derivative of in this one, so if you act on derivative on this one, phi I, and then what you get is as follows. So minus 2x mu. So this is an ordinary piece you get. Okay, so if you act, if you act the derivative on here, so multiply this one in here, this will see, of course, this one. In addition to this, this derivative c gives x. Therefore, this will give rise to the following term. Following term minus 2x mu down mu minus 2x mu down mu of phi, and also minus 2 delta mu nu x rho partial rho phi, and then minus 2 delta phi x mu down mu phi, and then minus 2 delta phi delta mu nu phi, and so on. Behave as like this. And in addition to that, you have this one too. So here, in addition to that, I think seems like my lecture note doesn't have this stuff. So far we just have derivative of this piece and this piece, and in addition to that, you need this piece. So therefore, what you get is that something like this one, minus 2 x mu acts on phi I. I think I'm running out of indices. I think I should use the rho phi I, And then you have a 2 delta rho mu. Sorry. Delta. Like this one. In addition to that, we have like this one, 2x rho, delta mu, s mu, so, and then 5. Okay. So these are the transformation. So certainly you can have this, if field phi satisfied under the transformation of the special conformal transformation like this way is called primary field. But if you act the derivative on the primary field and do the special, this is equal to special conformal transformation of this operator, derivative operator, then it gets really ugly. Okay, it gets really ugly. So therefore, in addition to this one, so this one and then which piece were there? So this one. And then also this one, okay, are the order piece we would expect to get. However, in addition to that, we obtained some lots of more extra term you obtain. Okay. So therefore, so this. Okay. And in addition to that, you can combine. So if you compare this guy and then this guy, so you can have an additional term like this. So. Yeah. So in addition to this one, so here, sorry. So additional term like this one, sorry, this one. So if you combine them together, you can conclude that this transformation phi has a conformation delta phi, but delta mu phi has a conformation delta phi plus 1. Okay. So you can combine this delta phi and plus 1, and then you can have you can conclude that this primary field if primary has the conformation delta phi, then delta mu phi has the extra piece plus 1. Okay. That's we can conclude from this transformation. So usually if this is the primary field, so this derivative of phi under the special conformal transformation, it gets really ugly. So this is called descendant. Okay. So this is called descendant. So if you consider the operator in a conformal field theory, this is like a clean transformation is really preferable. It's really preferable. That's why the primary field plays a very important role in the conformal field theory. And if you act derivative on keep acting a derivative on the primary field, you get that so-called descent. Okay, so that's what we need to Any question at this moment? So this is the one way to define a primary field. Okay, before, so that's a transformation rule we look at. But another way to look at this transformation rule is okay. I think I just did it too fast. Okay, I think I'll come back to this transformation a little bit later. And before that, let's look at the. So this is one way to define how to define primary field in conformal field theory, and this is how we define in the high dimensional field. But let's look at this, as I promised. Let's look at the 2D. Let's move on to 2D CFD and what's going to happen. So what is a conformal transformation? So conformal transformation is, as I mentioned last time, so it's derived by translation, and then so rotation or Lorentz transformation or rotation. And the scaling or dilatation, transformation and dilatation. And also, what was that? The special conformal transformation, or inversion. And how do you characterize a conformal transformation as follows? So if you consider the metric of the space-time, so if you consider the two Riemannian space, and then it's mapped to the two Riemannian space M and G are. So this is the D-dimensional space, and this is metric, and then you can just map the difference, so this is for diffeomorphism. So F is the, maybe I could call it phi or something, or phi or so on. And then you can consider pullback of the metric, pullback of metric of G prime. And then G prime, so essentially you just copy the metric information from here, here to the previous case. And if they are related by scaling transformation, this is called conformal transformation. So therefore, what's really happening is that so there's a big group of diffeomorphism. Diffeomorphism group of space-time manifold. Inside there, there is something called something Riemannian manifold. Inside there is a conformal transformation. Okay. So, conformal transformation is the diffeomorphism that preserves this property, which is a bit too abstract, but we can make it a bit more solid. So this is what is diffeomorphism? Diffeomorphism can be understood as a locally Fourier transformation. Locally transformation, Fourier transformation. And if we consider only the case R, D minus 1, and then A and mu. So the flat space case. So all the metric is the Minkowski or RD and delta mu. So this is the Euclidean case. So whenever we consider the curve background, I mean we can consider curve background to consider the rod anomaly and so on. But that for time being, let's consider only the plot metric for time being. So then the new metric you will get is that the pullback metric you will get is that the air rho sigma is partial. So this Fourier transformation x prime of mu x of whatever x. So the Fourier transformation you get is eta rho sigma partial prime rho divided by partial x prime of sigma partial x mu of lambda of x and eta mu. That's the Conformal transformation you get. So this is the pullback metric. So this is essentially corresponding to phi star of G prime. Essentially, you just get the Fourier transformation metric here. That should be proportional to the original metric. So that's the proportional transformation. And proportional means that up to some scalar function, lambda. That's the transformation rule, which we will. Okay. So this is the transformation rule. And essentially what's really happening is that the map you get is something like if you just have this kind of the grid is mapped to, like, for instance, if you map like this way. And so on. So always it should preserve an angle. So conformal transformation should always preserve an angle like this. Always has to be orthogonal. Okay. But the length can change. Locally it should preserve the angle, but locally it can just change the length of the the length of it. So then okay, so that's how you define the conformal transformation usually. And then if you look at the local transformation, x prime of sigma is x rho plus epsilon rho plus order of epsilon squared. Then this transformation, this equation can be just rewritten as follows. So just plug that into here. What you get is that the partial mu epsilon mu partial mu epsilon mu is equal to k of x a mu, where k is equal to 1 minus lambda. Does anybody wants to derive this one? Or can you see that? Is it easy to see that? I mean, if you plug that there, so what you get is essentially eta mu nu plus partial minus oh, I told you wrong, so this is not true. Lambda x minus, it should be plus. Okay. essentially this one, and plug this one into here, you get this relation. Fine, and the contract with the area mu, what you get is that rho epsilon rho is equal to k of x times t. Times t. And then right hand side you have to multiply by 2. Multiply by 2. So if you just contract this is the dot of epsilon, if you get dot of epsilon and then another dot of epsilon, which will give you 2 here. And area contraction will give you trace of area is will give you d. Okay? Is it okay? Fine. So then you can just plug that into here. So this means that the k of x is equal to 2 over d. That of this. Okay, you can just plug that one into here. What you get is that the down mu epsilon mu plus down mu epsilon mu is equal to 2 over d down epsilon area mu. Okay, that's what you get from the analysis. Fine. And you can do the further implementation of this one. Implementation of the transformation is that the here, if you further act on into what the say mu here, then what you get is that the partial mu okay, that's what you get. So you can easily see that. Is it okay? So you just multiply down mu, so you just contract with this guy, and also this guy contract with this guy, that will give Laplacian here. And then down to mu acts on, so therefore this guy contract with the area mu will give you this guy. Okay. Is it okay? Is everything okay? Okay, and let's massage this one. So this term is equal to this term. So therefore what you get is 1 minus 2 over d is equal to okay. Which do you prefer? I prefer in this way. Two over d minus 1 is equal to delta epsilon mu. Not delta. Laplacian of epsilon mu. Okay. Is it okay? So far, all the transformation is clear. No problem. Fine. So what's special of d equal to 2? If d equal to 2, left hand side is equal to 0. So the reason why you get the d equal to 2, if you put d equal to 2, this equation becomes the Laplacian x of mu is equal to 0. Okay. So therefore, that's why d equal to 2 is very special. This is a very special. Okay, it's very special. Okay. So d equal to 2 is very special. Okay, let's look at the arbitrary dimension. D is greater than 2. Then what you we get is that the father acts on this one to for the derivative on times delta nu. What you get is del mu, del nu, like this one. Fine. So interchanging of this one. So and then you just interchange the mu and nu. Okay? If you interchange mu and nu, what you get is at the same piece. So 2 minus the left hand side does not change, But here you have delta mu, epsilon mu. Okay? If you add them up, we can use this identity. Okay? If you add them up, we can use this identity. Then that will give you the following thing. Eta mu nu Laplacian acts on d minus 2 delta mu del mu acts on del mu delta mu. So that's what you do. And if you take a trace of indices, so if you take the n mu nu, what you get is that as follows: d minus 1 acts on Laplacian delta epsilon is equal to z. That's what you get from here. Okay. Fine. So, which means that this guy is equal to 0. Okay. So another useful thing is that we can just use the acts on this one. So another thing, if you look at this one, it acts on the alpha derivative indices dot rho plus this equation. Acts on this one, and then what you get is as follows. Okay, so that's what you get. And you can just shuffle. You can shuffle rho and mu by simplicity, like this way. Become cyclic before cyclic. And I call it number 1, number 2, number 3. Then if you do the computation 1 minus 2, minus 1 plus 2 plus 3, what you get is that the 2 times del mu epsilon rho is equal to 2 over sigma minus eta mu nu del rho. I mean, it's just a computation. Like this one. So that's another equation you look at. Right? Fine. Okay, so then let's look at this equation. So let's look at this equation. So this is equal to 0. This is equal to 0. Equal to 0. Therefore, we plug down into here. Laplacian x on this one is 0, right? Okay? Is it okay? Laplacian x on this one is 0. So which means that this quantity is equal to 0. Okay? Is it okay? Fine. So therefore, this means that they at least, so this means that they are del mu, okay. So this means that this means that the del epsilon has to be at least linear. Okay, so it's a scalar quantity. It's a scalar quantity, so therefore it's some scalar times vector times x mu. Okay, because it's quadratic derivative should analyze this guy, so therefore it has to be at most linear in x. Okay, at most linear in x. Fine. And plug this one into here. Okay? If you plug this one into here, del dot epsilon is this one. So then plug this one into here. So then what you get is that the del mu epsilon rho is something like, sorry, this is 2 over d. 2 over d. Is something like a constant. It should be equal to constant. So 2 over d, and then what you get is that the minus eta mu b rho plus eta rho mu b nu plus eta nu rho b nu. Okay. So it's independent of independent of x. Is it okay? So far, so good. Okay. So this means that so at most this epsilon can be quadratic in x. Okay. So if you have two derivatives, it becomes constant. So therefore, if you have epsilon rho, epsilon rho of x has something like whatever x squared plus what is it, x squared x rho. If you have it contains this term, okay. If you have twice of derivative, still it depends on the x, right? Still depends on x. So this never happens. It's never happened. Therefore, it has to be at most quadratic. Okay. So therefore, we can just mention that this. So this is never happened. It's never happened. So therefore, epsilon rho has to have the following thing: a rho plus b rho sigma x sigma plus c rho mu x mu x mu. So that's what we need to import. And then since if you add the twice derivative, you only see this term. I think I call it C here. So C rho mu is in fact should take the following C rho. So if you plug this one into here and just look at the symmetry of this one, this has to satisfy the following thing. C rho mu. Okay, so that's the what you need to import. Okay, so it has to be symmetric on the mu and nu. Because I mean, if you act nu first, mu fast, it's the same as act on mu first. Okay, that will give you this symmetric. Is it okay? Fine. And then let's look at what it means. So let's look at what it means. So what this term means? What this term means? Translation. Good. Thank you very much. This is translation. So this means the x row moved to x row plus arrow. Okay, so that's that translation. Fine. This matrix can be decomposed two ways. This is the some symmetric matrix, which is eta rho sigma, with a symmetry matrix, with anti-symmetric matrix rho sigma. Alpha. Okay. Or maybe X. Okay, we can always do that. Decompose matrix into symmetric part and anti-symmetric part. Okay, so this is a symmetric part and anti-symmetric part, and you can always just make it proportional to the for symmetric part can be proportional to this. That's order eta rho sigma, just sigma. Metric, Minkowski metric of this one, and then this anti-symmetric part can it can be proportional to this epsilon r thing. Okay. We can always do this kind of transformation, and in fact, this guy. What was it? This one is the dilatation. So as you can easily imagine, x row is mapped to x row plus a times x row. Okay, or maybe I think I should alpha times x row. Okay, so this is a dilatation, and of course we know this guy will give you what? This will give you rotation. This will give you rotation. Okay. That's the case. And the last piece is much more subtle. Subtle one is you can easily imagine. So this row mu can be just write down as follows. I think I can erase around here. If you plug only this one, if you plug this one here upstairs, what you get is as follows. C mu rho plus eta rho mu f mu plus eta mu f rho minus eta mu rho f mu. Okay. Where f is 1 over d. Rho mu. So plug this one. Plug this one. You plug this one. And of course you set A and B equal to 0. Plug this equation A set B equal to 0 and just plug this one into here and do the computation. Do the computation, you get this one. You get this one. Okay, and then this one is in but will give you the following transformation: x prime mu is equal to x mu plus 2 x of f x mu minus x dot x f mu. So just plug this one. Now plug this one into here. Oh, what's that? Here. Okay. If you here and just write down explicitly, then you get this equation. Okay. And this is the familiar piece of the transformation rule. This is the special conformal transformation. Okay, special conformal transformation. That's what how you obtain. So, is it okay? Is everything fine with you? Okay, that's how I obtain so what we did is that as follows. So you just start with this usual transformation rule. This eta mu partial x prime mu x rho partial x mu partial x sigma and lambda of x eta rho sigma. Okay, rho sigma. From there, from this equation rho, one can just derive this x prime should be composed by translation, dilatation, and then rotation, and the special conformal transformation. Okay, so that's what we did for this definition. When d is equal to greater than 2. Okay. So now we move on to the two-dimensional part. Two-dimensional part. So two-dimensional. So the special thing two-dimension is this equation. Okay, so this thing can be understood as follows. So this one can be understood as follows in two dimensions. So this guy, so nabla is the partial unit. So this means that the if you consider del t, it depends on signature square plus del x squared. Okay, so this is the case in two dimensions. So I put that x0 is equal to t, xy is equal to x. Okay, that's what I did. So this also epsilon mu. So which means that this one can be understood as minus of delta t plus I delta x. And then delta t. No, sorry. So I don't need that. Plus x. Acts on. So therefore, this means that delta t plus delta x acts on delta t. Not delta t delta x acts on epsilon is equal to 0. Okay, so that's what we mean. So therefore, the epsilon, where epsilon only depends on either t plus x or epsilon depends on t minus x. Okay. Then this will be satisfied. Okay. Is it okay? So if t plus x is a case, if this is a case, if this derivative acts on here, you get 0. Okay? Or if t minus x, if only if t minus x dependence, this derivative acts on this one is equal to 0. Okay. So therefore, it either depends on this combination or a plus combination or minus combination. That's why in two dimensions. But okay. Now, if you move on to the Euclidean, so this is the Minkowski case. And if you go to the Euclidean case, it's much more simple. Essentially, this one becomes plus sign. Okay? It's plus sign. Okay. Therefore, if you put that I here and put the I here and a plus sign, this will be satisfied. Okay, is it okay? So far, so good. Well, therefore, there's an I here, and also there's an IX here, minus IX. Okay. Is it okay? So therefore, if you call T plus Ix as a homomorphic field, Z, well, this is anti-homomorphic Z bar. Okay. So Z is the homomorphic T plus Ix, or Z bar is T minus Ix. All the homomorphic functions satisfy this equation, satisfy this Laplacian is equal to 0. So this means that there's as follows. So either homomorphic transformation or anti-homomorphic transformation will satisfy our conformal transformation. In 2D, in D equal to 2, in D equal to 2. That's the main property, key property in D equal to 2, D equal to 2 case. Okay. And so therefore, the transformation rule of the field can be understood as follows. So if you consider Z prime, Z is not to Z plus epsilon of Z, which is a homomorphic transformation, Z plus sum of En, n rounds for Z. It's just a Laurent transformation, En plus 1. Okay, so it's just a Laurent transformation one can do. Like this way, if you around the, so this is a Laurent transformation. Around Z equal to 0, equals Z. Then, so this field is transformed as follows. Which is equal to 5 prime Z prime minus epsilon of Z. And this is equal to minus epsilon Z and now phi. Okay. And then this can be understood as follows. Minus squared sine. Minus Cn plus 1 at some point. Okay, so this del is the del dot 0. Okay, I only look at the holomorphic part. I ignore the holomorphic part. Okay, that's what you get. So I just epsilon 0 is just a higher Laurent expansion around z equals 0. Okay. So then wait. It should be. So you get this. Okay. And I call this one generator is Ln. Okay. So this is there are infinite many. So now it's an infinite many generator in 2D of a conformal transformation. Because it's just any transformation law. So for instance, so any epsilon n, so any constant for any n, integer n, you can have a non-trivial epsilon n. Okay. So therefore there are infinite many generators. Okay. For conformal transformation 2D. So for instance, I mean epsilon z can be whatever. I mean, in my notation, something like that. Okay, z to the 1, epsilon 0, and then epsilon minus 1, and then epsilon minus 2, z to the minus 1, plus epsilon 1, z squared, plus blah, 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 and dot, dot, dot. So I just get rid of 0 actually at this moment. So yeah, so I just don't care about the so this transformation is not it's singular the 0 0, but I don't care at this moment. It's singular. So there are infinite many generators which is generated by this L1. Okay. This L1 satisfies so L1 I define as z to n plus 1 in a holomorphic derivative, and this will satisfy the following computational relation. Is equal to n minus n, L n plus. So this is just a direct consequence of computational relation. And this is complete algebra. So naive analysis of the conformal transformation 2D is already infinite dimensional. Okay, already infinite dimensional, and it's satisfied with algebra. And then we can take a look at what kind of transformation will give you what we know about the other conformal transformation. So later, this will be modified. So I think many of you already know, or many of you already expect to what's coming. So as many of you always expect, this will give you this. Equal to n minus n plus e over 12. And squared minus 1. Or, I mean, it depends. I don't know how. Anyway, so it's a correct equation. Delta n plus n. Okay. That's the. So here, this one is called central charge. And this one is called central extension. So central extension of the bit algebra. And then everything is called USR. USR, right? Okay. Do you know nationality of USR? Where is he from? And when does it appear in the literature? Do you know that? he's an Argentinian. He's Argentinian. And I think as far as I recall, this diagram here, this as far as I understand. Okay, I may be wrong, but anyway. That's like this. Let me a little bit move on. The question is, previously we know the translation, rotation, what was that? Dilatation, and special conformal transformation will give you the conformal transformation when d is greater than 2. But 2 dimension is somewhat special because of the equation is somewhat special. And let's see how we get the subalgebra of this bit algebra. Fine. Okay. So here, when I talk about this one, so I don't care about what happens z equals to 0. So we don't care about when z is equal to z is singular. Z equals 0 is singular, no. But let's care about which generator are well defined at z equal to 0. So if you look at this transformation, okay, if you have a say n ln n less than 1 are singular at z equal to 0. Sorry, minus 0. Okay, that's we know. Because I mean, it has z to the z inverse. So when z equals 0, this is divergent. This is divergent. Okay. Are you guys following? How about z equals to infinity? Which generator well defined z equals to infinity? To see that it's better to do the following transformation. Okay. So essentially, what we are doing is some Riemann sphere. Riemann sphere, which is S2, and then on z equal to 0, z. So this is a complex plane C, and z equals to 0. This is a good coordinate. Z equals to 0. So z equals to 0. So you can just map this infinity from how to say normal pole to the each point in S2. At each point in S2, you can just map to the C, but except this north pole. The north pole is just correspond to the how to say to the infinity of C. Because I mean, if you just go to the closer to north pole, everything goes to the infinity, right? Infinity. So therefore, north pole corresponds to infinity. So which is C equal to infinity. But to go to the good coordinate on around north pole, you just put the different it's called stereographic projection. You just take the south pole to just map to this point in south pole from south pole and point in S2 and then map to the like you just one-to-one correspond. That is just a translation. W goes to 1 over 3. Okay. So then, if you do this transformation Wn, Ln can be understood 1 over W. N minus 1 del W. Okay. Is it okay? Because I mean del W is equal to Z del W del Z is equal to del W. What was that? Z and del W. And this is equal to, you just plug this one into here. It's just W is equal to this one. So therefore, this is minus 1 over Z squared. Del W. Okay. Okay. And plug that one into here, you get this one. You get this one. So this means that the L n greater than 1 are singular at Z equal to infinity. Okay, Z equal to infinity. Fine. So therefore, all the generator which is globally defined on this Riemann sphere is that the only L minus 1, L0, and L1. So only the generator which is globally defined everywhere on the Riemann sphere is L minus 1, L0, and L1. Those are well defined. This Riemann sphere. I will write down the C plus infinity. Plus infinity. Fine. So L minus 1. So this one is just del Z, and this one is Z del Z. Okay, and this one is Z squared del. And then there must be some negative sign in both. Negative sign, negative sign, negative sign. Fine. And you can consider the corresponding anti-homomorphic part of this. So you can easily see this one. So this one will give you a homomorphic translation. And this one is also very, very easy to guess. So this one is it's very similar to I already erased. The last, so we have this one, right? So E is equal to A plus B mu. So E rho. Epsilon rho is equal to A rho plus B rho mu x mu plus C rho mu x t. Okay. This is very analogous to L minus 1. And this corresponds to L0, and this corresponds to L1, as you can easily guess. See what's going to happen. So what was this guy? So this is a 2 by 2 D by D matrix, and the symmetric power corresponds to what? Symmetric power corresponds to what? You just decompose symmetric and anti-symmetric part. Symmetric power corresponds to what? Dilatation. Anti-symmetric part is rotation. Okay. So to see that, so we would expect that a similar thing happen here. To see that, you just rewrite Z is equal to R times E to I set. So you just use the polar coordinate. So there's a complex plane C, and there's a sphere, and this is the R direction, and this is the theta direction. You consider, and then this one can be written. Z can be written like this way. In that case, L0 is just that if you do the transformation on half R del R plus I over 2 del theta. Okay. Del theta. And if you look at the anti-homomorphic part, it's just the same thing. Minus I over 2 del theta, which means that the L0 plus L0 bar is R del R. Okay. And the L0 minus L0 R is equal to del theta. I or something like that. Okay. And then you can easily see R del R is just R del R is just how to say the vector field is something like this one. Vector field. So yeah. So this is the dilatation, scaling transformation. You just change the radius of the circle, and then the Gaussian. So this corresponds to R, delta R, and this the Gaussian is just a rotation. It's a generator of rotation, as you can easily see. Okay. So now this is the dilatation, and this is rotation. Okay. Now this guy. So what's left is what? What's left is what? What is left? Okay, special conformal transformation. Good. Special conformal transformation. Let's take a look. But we don't need to do that actually. This L1 is the minus c squared delta c, right? And use this transformation rule, okay? Plug that into here. Then what you get is this is delta w, okay? Delta w. Is that okay? So therefore, it's just a homomorphic translation in w variable. So this is z variable, this is w variable, this w equals 0. And it just shift off this translation in homomorphic way. So therefore, this should generate the w goes to w plus some variable c, homomorphic translation A. Whatever it's okay. Okay, and then let's do the transformation. So this one is 1 over z is 1 to z plus c. And if you take the, so this is z prime is equal to this one, which means z prime is equal to z over z plus c. Okay. Fine. And this really corresponding to special conformal transformation. So you can see, right? You can see, right? So you just start with whatever variable z and map to 1 over z. 1 over z is a kind of inversion, homomorphic inversion, and map to c is 1 over z plus c. And take the inversion, and you get a z over z plus c. That is your z prime. Is it okay? Yeah, of course, this figure is not correct. I mean, when you take 1 over z in homomorphic way, it just actually go to here. I mean, angle will change. So, but I think it's just this is not correct diagram. But what we are doing is homomorphically doing special conformal transformation. Homomorphic. Okay. Fine. Let's take a break. Yeah, so let's take a 10 or 15 minutes break, and then we will resume. Okay, shall we start? Okay. So the first part, first part, before going to this kind of transformation, I just talk about transformation of field a little bit, but that is actually too fast, so I just changed my plan actually. Fine. Let's see. Let's how we proceed. Maybe I can show you something. Oh, does anybody have something adapter between this guy and this guy? No, nobody has it. I forgot to bring. Maybe nobody has it. Yeah, unfortunately, I didn't bring it today. Oh, okay, then. That's one. Then maybe next time. Maybe next time. What to bring? Oh, then let's see. Okay, let's do the following exercise. Before going to meta theorem and so on, let's see. Or doesn't it? Okay. You guys just only brought iPads, right? You guys do not bring the laptop, no? Do we? Do you? I'm asking my students, but sorry. Then no. So, 那我想你看这个视频啊，去。但是没办法，下次我再把这个。Fine. Let's do the following exercise. How to transform, be transformed. How does be transform under the transformation? Okay. So at the first 30 minutes of the sort of transformation of the field, and then what we saw is that the P acts on. So P mu acts on operator. This will give you something like I del mu operator. I operator. Yes. That's the commutation relation between operator O and P mu. That's the. So this can be understood as a Heisenberg picture. Heisenberg picture. So this guy. So for instance, I mean, in Heisenberg picture, operator depends on time and so on, right? It depends on the. I mean, to go to Schrödinger picture, I mean, you just need to. I mean, you need to do this kind of like sandwiching between time translation and so on, and so on. So the H or T depends on this one. Is the delta T, right? Is the like this way. This is what you learn, right? In English quantum mechanics. Okay, so this is what you need to do. Fortunately, my lecture note is not correct. Okay, and then, so what I wanted to explain is that this J mu acts on OI of X is equal to X mu OI of X minus I S mu J I and OI of X. And then the first 30 minutes, I derived this one for OI is equal to gauge field, or like a vector spin one field. Okay? That's what I did. So this transformation depends on this matrix. This was spin matrix. Depends on OI. Depends on OI. For instance, yeah, as I mentioned in the beginning of the lecture, so spin one field we need to write down. I think it's just a combination of delta and A. As you recall, delta rho mu eta mu sigma minus delta rho mu eta mu rho. Yeah. Sigma. Like this way, and A sigma. That's what we have. That's what we have, and plus minus. I don't remember which one is finished. In the case of spin one field, do you know what if you spin one half field? Oh, how does it look like? That's what you learn in the quantum field theory. Do you remember? How does Dirac field will transform under the rotation? Do you learn? Do you remember? How do you express this as mu nu? Does anybody remember? Seems you remember. So can you speak up? Essentially, this S mu nu is proportional to computational ratio gamma matrix. Essentially, the gamma matrix is, as you recall, I mean that defined the Dirac equation. I mean gamma mu. So essentially, it's proportional to commutation. It has to be the antisymmetric because of the rotation antisymmetric. But essentially, you need to. So I don't remember the precise number here, but it's just a computational relation for spin. Okay. Fine. And Dirac action operator I in the Heisenberg picture is given by minus I x mu. Plus delta I and OI. Okay. And in any dimension, D is the any dimension, any D, so that you use the special conformal transformation to define. You can define a so it's called primary field. That's what I wanted to explain actually in the first 13 years, but I failed. But anyway, so if this satisfies for I or x, that's one definition. But one way to define a primary field. X mu, S mu nu, Gen I or Gen. That's one way to define primary. Primary operator. Sorry, I should mention that it's not primary operator. Definition. This is definition. OI. If the under special condition. And as I mentioned, what I want to explain is that so this guy, if OI is primary, the alpha mu or alpha the K mu K mu and mu is argument. Oh my goodness, how do you spell it? Argument. Transformation rule is very argument. It's much more complicated. You just need to add some derivative on this computational relation, which I don't want to do for you. So in this case, this derivative act on primary field is called this one. And in particular, if you look at this one, K mu acts on operator at the zero. When at the origin, this term is vanished, all time is proportional to at least x. It's a quadratic in the first term, but the second term is linear in x. Therefore, this is equal to 0. At x mu is equal to 0. So, for example, for primary operator acts on if the special conformation acts on primary but at the origin, is when you get 0. So that's the one way to define the okay. Fine, and then we can move on. So that, for example, scalable. Okay, so for instance, scalable of x. So in this case, the s mu nu is equal to 0. So s mu nu equal to 0, then the things are much more simplified. Level 1 descendant. So it's called level 1 descendant. Is the p nu axon operator of x. Okay, so this is the p nu axon operator of x. It's like this way. Then what you get is as follows. So it just can you act on this operator p nu? So this can be corresponding to a dimension from here. From here, it's just a derivative axon operator, right? So this corresponds to operator partial nu axon O of x. And then O is a scalar, so you can ignore this S and so on. And you can do the following thing. Is the operator of x acts on this one, and which is the k mu, and then p nu of O acts on x is this one. Fine, and this one is equal to confused. And then let's see. Sorry, I got confused. I think my lecture is something strange. Sorry, just a moment. Wait. What's going on here? I think what's going here? So this should, I don't know, so in my lecture of today, this should correspond to P nu acts on K mu over operator of X. Let's see. How do you get this one? So it's just K mu acts on liquidity convenience. Sorry, I got confused. So, sorry, I don't know the step, but from there we get 2x means x row, partial row, x squared minus x squared, partial mu, down mu, operator of x, plus 2x mu, down mu, 2x mu, x mu, operator of x, and then plus 2 delta mu nu x row the row of x, and then plus 2 delta 0 x mu down mu over of x. Yeah, I think it's just x on 2 times delta 0 delta mu over delta x. Right, so okay. I think this one is just you just ignore S mu here. Ignore S mu and the x derivative on del mu. So you just multiply this one. So it's just this one. Okay. And if you take the x goes to 0, so then you get the k mu and the p mu and operator 0. And this is equal to 2 times delta 0 down mu operator option. So this is what you get. So once you set x goes to 0, this term is gone, and this term is gone. X equals 0. So this term is gone. This term is gone. So what's left is this. So this is yes. So what I did this one is just you act on derivative of the del mu and ignoring this term because it's scalar. Because of this assumption. It's scalar, the matrix is 0. So now for this is non-zero if delta 0 is non-zero. And as we will see that the delta 0 is essentially is the vacuum, and delta 0 is corresponds to vacuum. So therefore, I mean, essentially, so this is the way to see that this is not primary state. So the primary state always get the 0 once you special conformal transformation acts on the operator at 0. But here, usually generically you won't get 0. You won't get, for descendant you won't get 0. Because usually this delta is non-zero. Okay. This is how you see that. Okay, let's do a bit more exercise. And last time we looked at the computational relation. So this is for generic case, generic dimension. I don't focus on d equal to 2. So this dilatation d acts on p mu. So last time, as I mentioned, this one is equal to minus I p mu, and d acts on k mu is equal to plus I k mu. Okay, they have the opposite charge. The k mu and the p mu are okay. And let's look at what's going to happen. D acts on, as I mentioned, d acts on operator O. Okay. Or I is 0. If you look at this one, let's look at this one. So what would you get? This one. Did I erase already? No, I don't erase. So if you set the x equal to 0, this is equal to del I maybe it's up to some sign. Up delta I or I. Okay, so that's what you get. Is it okay? The first term is. So you can ignore this one, what's left is this one, okay? Is it okay? Or I see. How about the descendant? P acts on OI and 0, okay, and D, okay? So if P acts on operator, what's going to happen is the following. So you can use the Jacobian identity to show this one is equal to d p mu acts on commutator for I0 p mu acts on d and OI0. Okay, so that's what you get. Is it okay? So you know Jacobian identity, right? Jacobi. You know, right? A, B, C plus B, C CA plus CAB is equal to 0. Okay, so this is Jacobian. And if you use this one, you get this one. Okay, you get this one. And now we know this one is equal to what was it? So this guy is equal to minus IP mu, right? Minus IP mu. Okay? Minus IP mu. And we know this guy is equal to minus I delta I OI. Okay? And the P mu acts on OI as like this way. At the end of the day, what you get is that this one is equal to minus I delta I plus 1 delta I plus 1 for I. Okay. Fine, is it okay? And I clearly make a torsion, right? So this is P mu and OI. Is that okay? So I just combine this guy and this guy. Okay. Is it okay? So this is P mu acts on OI, so that will be 1. And this guy, I'll give you delta I. So what is the conformal dimension of this descendant? P mu acts on OI. What is the conformal dimension from previous case? How do they change? What? Yeah, increase 1 dimension. So previously, conformal dimension delta I, but once it acts on P mu, the conformal dimension will increase by 1. Okay? Is that okay? So therefore, descendant has a plus 1. Level 1 descendant have a conformal dimension. Let's do the same exercise for K mu. What's going to happen is as follows. Okay. So let's do the following exercise. D acts on K mu and operator I on 0. And then if you do the same exercise, what you get is delta I minus 1 K mu and then OI on 0. Here, because minus sign, because the sign is different. Okay, is it okay? And I assume this guy is not primary. Because I mean, if it is primary, K acts on O is what? K acts on O primary is what? 0. As I mentioned here. So therefore, we can assume this guy is primary. Okay. But this is true. So therefore, P mu increase conformal dimension by 1 and decrease K mu decrease conformal dimension by decrease and increase. Okay, that's very simple. And then, what was that? What I'm trying to do is that so for primary state, so what we needed to do is that one way to check the commutation relation is that so as I mentioned, I P mu total K mu is equal to 2 eta P mu D plus 2 K mu. Okay, so we have. And then, so we need to check that the difference equal to, by Leibniz rule, by, not Leibniz rule, Jacobianity, I times, so this is minus I times OI of x and P mu and K mu, and minus I and then K mu for I of x and P mu. That's how it works by Jacobi identity. So this is if you use what I'm doing. So this is equal to pk p mu k mu axon or I. So this is Jacobi identity of this one. Jacobi identity of this one. And then it's a good exercise to check is just plug that into here. What you get is that you should get a 2a and mu d plus 2 j mu of axon operator or x. So that's the case. Then, so it's an exercise. This is actually homework of the first homework that if OI of x is a primary operator, which you know that how this k axon on. Okay, I already give a definition how k axon primary operator. That's the definition of primary operator. This identity is satisfied. Is satisfied. That's the exercise you need. Okay. That's what I wanted to explain. Fine. So that's how this generator of conformal translation acts on the state. Okay. Another thing is that we can just consider the vacuum state space in Minkowski, which are low-length invariant. Okay. So Hilbert space, in Minkowski's conformal filter. Conformal CFT is defined as follows. So the backing of P mu should be added by, so it should be J mu acts on backing in C. All generator acts on the backing and others D. Okay. The backing should satisfy. This means that the backing. This is the vacuum. Vacuum satisfy the conformal symmetry. Okay, that's it. Furthermore, we'll just define as follows. And then we need to impose all physical state and an inherent state. So this is vacuum and all physical state should satisfy the following conditions. Physical state phi should satisfy this inner product. It should satisfy unitarity, positive definite. This is a positive definite. So unitarity, or this is positive definite. That's the assumption we assume. Yes. However, often instead of Minkowski, so this is the Minkowski vacuum, or Minkowski vacuum, or free vacuum. This is the so this zero is called Minkowski vacuum. Minkowski vacuum is also used so-called conformal field theory, CFT. In here, usually, in addition to that, okay, maybe I can say a little bit more. So in Minkowski space, so this is important thing is Minkowski. Minkowski space, we further assume the following thing: Hermitian conjugate. In Hermitian conjugate, in Minkowski space, we just in state space we assume this one. It's that is equal to P mu. I mean, just the self, how to say, is everything Hermitian in J mu, and D dagger is equal to D, and K mu dagger is equal to K mu. It's a Hermitian. All the conformal symmetry. This means that the conformal symmetry is Hermitian. Hermitian order. However, we often do the following thing. The conformal field is cylindrical space. It's called radial quantization. We will see as the due course. So a CFT in cylindrical space. Cylindrical space-time, which means that the RT plus S D minus 1. So this is the space we consider, usually often consider. So the here, everything defined by S, this is schematic diagram, is S D minus 1 diagram, and time direction is like this. So that's the like high dimensional cylinder. Okay? So at each slice, each space, this is time direction. You can consider time direction. In each slice, you have a sphere. Each slice, you have a sphere with D minus 1 dimensional space. Okay? We consider such a space-time and do the consider conformal field. So in this case, okay. So in this space-time, what's going to happen is as follows. In this space-time, we consider D. So in this case, okay, you can just map this one. So you can do the conformal transformation. Now transformation is the following: R, how to say, R D space, get rid of 0. In that case, we just get rid of origin and consider the R D place. Okay, and each how to say, the circle surrounded by origin, each S. So this is the S D minus 1 dimensional sphere around the origin. Is mapped to this one is mapped to this part. Okay. And then following thing, likewise, if you just have a bigger circle, and and then you just map to like this way. Is the next. Okay. So in this way, in this way, so this radial direction. So this radial direction is mapped to the time direction. In time direction. And then this at the origin. So at the origin is to get rid of. It's really becomes so at the origin. So at the origin, close to the origin is the okay. So that this t goes to minus infinity, corresponding to this whatever x is equal to x goes to 0. X goes or r goes to 0. Sorry, r goes to 0. Okay. So this is the r direction. R direction. This is the r direction, and this is t direction. And you can map one-to-one correspondence between this cylindrical place and this the RD. Get rid of this origin. Okay. So this is actually in the conformal transformation. As you can easily see, that the angle is preserved. Here, angle is preserved. It's always angle is preserved. Okay. So radius direction is always the orthogonal to the. Okay. So one can consider such a space-time. So in this space-time, this is no longer hold. So in this space-time, this is no longer hold. This is the only Minkowski space. This is so in cylindrical space. This is not true. This is not true. And in fact, what's not true is that follows. Maybe so that this part is and this part is not true. So I just want to write down. Therefore, in this the mapping, so it's called often called radial quantization and so on. Safety. So the Hamiltonian, so the dilatation operator. So here in right hand side, dilatation is really scaling. The circle become bigger, the sphere become bigger or shrink. This D operator is really D operator here. Dilatation operator is essentially R delta R. Most likely you have some number here. I don't know the number. So D, it becomes the Hamiltonian of this cylindrical place. This Hamiltonian is they just give you time translation. This saving cylinder, Hamiltonian of cylindrical space. Okay. So as you can see, so time translation is just time translation. Hamiltonian will give you time translation, right? So this is the time translation map this green sphere to purple sphere. Even this here is also dilatation is map this green sphere to purple sphere. Okay. Therefore, dilatation here becomes Hamiltonian of cylindrical space. Okay, so that's the difference, main difference. Now D become H instead. Okay, and then we know that the so we know that the H, so therefore now we have this kind of relation is equal to P mu, and HC acts on K mu is equal to minus K mu. Okay. So that's what's happening in here. And also K mu analyzes the primary state. And the P mu creates a descendant state. That's as before. And then now also vacuum in this cylindrical space, I call it omega. So it's a different from the vacuum in Minkowski space. Okay, vacuum in Minkowski space is just consider R. So the difference is that vacuum is defined here. So vacuum is defined in just R d minus 1, comma 1. And each space is just this space. This is R d minus 1. And times is this R time is here, like this way. So that's, and the vacuum is defined at each slice. Okay? At each spatial slice. This is defined in like here. But here, the state is defined each sphere. So that's the difference. So each sphere here, the state is defined each sphere, whereas this Minkowski space is a state is defined spatial RT minus 1. Okay? So therefore this vacuum 0 is different from vacuum omega. That's an important difference. And there, so we assume P mu, another is omega, K mu, another is omega, and J mu, another is omega. Like this, we assume this is lowest energy vacuum is the in cylindrical space. Okay. And since we know, how about the d axon omega? What would you get? How do you get this one? Act what? How does it act? So since we know the P mu and K nu is 2 times A mu nu d plus J mu nu. Okay? Left hand side axon of this cylindrical vacuum is 0 because P and K axon 0, right? And J axon 0, right? As analyzed vacuum. So therefore this should analyze vacuum. And this is equal to Hamiltonian. So it's a Hamiltonian, okay, minus I don't remember. E minus I, okay. So that this is the lowest energy, so the lowest energy state in this cylinder, okay. However, important difference is as follows. So important difference is Hermitian conjugate. That's a different place. So important difference is that the J mu nu, the rotation of the sphere is just as before. J mu is a Hermitian. And also we want to have the time translation. Time translation is HC. Time translation is Hermitian. That's what we want. Okay, that's what we want. This means that those are Hermitian operators, but the consequence is that this one is equal to, since HC is equal to, what did I define C? So HC is I times D. So therefore I times D dagger is equal to I times D, which means that the what was that? D dagger is just minus D. Okay. Now you get a sign. Okay. So in the cylindrical space, D dagger is minus D. In this radial quantization, or it's called cylindrical space, in Minkowski space we put this one is equal to this one, like this way. In Minkowski space. But the cylindrical space, the D becomes anti-Hermitian. Okay. It's anti-Hermitian. Fine. The consequence that we need to impose P mu dagger is K mu. So consequence of that, we need to impose this condition. So as you can easily see, so let's look at this example. So this is the I times of this one. Sorry. I times of this one is equal to now delta mu of this one. Fine. Okay, so then take the dagger of this one, of dagger and dagger of this one. Fine. So we know this one is equal to minus 2 delta mu d plus j mu, right? J mu. Is it okay? Is it okay? So you have a minus sign. You get the minus sign because of these d daggers. The left hand side, now if you take a dagger, so this is minus I, and then it's a dagger means the P mu, K mu minus, what was that? K mu, P mu, dagger. Okay, dagger, right? And dagger will exchange the commutation relation. So this one is equal to minus I, K mu dagger, P mu dagger, minus K, minus K, P mu dagger and K mu dagger, and we impose this one. If you impose this one, this is equal to K mu and P mu minus K mu and P mu and minus I. This is equal to, and this is equal to what? This is equal to I times minus I times P mu and then K mu. Okay. Okay. Is it okay? So far it's okay. And this is equal to minus. So and this one we know that this one is equal to 2 times delta nu mu d plus j mu and down. Is it okay? And how we know j nu mu is antisymmetric under the exchange of mu nu. So therefore it should become minus times minus is equal to plus j mu nu. Okay, so therefore it's, but the first term is just delta mu nu is just symmetrical. It's okay. So therefore this condition is consistent. This condition is consistent with the what I impose here. What I impose here.
Excuse me.
Yeah.
Because J dagger equal to is that from as d minus y as option.
Could you repeat again?
Where do dash J dagger equal to J?
This one?
Yeah.
This one, this one, I mean, just give you the rotation, the symmetry of the symmetry of space-time. Symmetry of space-time needs to be unitary. So that, I mean, generator of rotation needs to be unitary. So therefore, it has to be Hermitian. So its time translation also needs to be unitary transformation. So you can go back and forth. Okay. So you can do the, how to say, anyway, so inverse matrix you need to do, unitary transformation you want to have. But in that case, you have to impose this condition. Okay. Now, but if you impose condition, P mu dagger should be become K. So that's a totally different from quantization in the just order plus space. So cylindrical plus radial quantization is different. Okay, fine. Now I'm going to the so-called state operator correspondence. fine. So I can erase this. Okay. So now, so we just impose so-called state operator. Oh, okay. So it's a good place to define. So since in the space-time, so what we can do is that the operator O of the time infinity can be understood as the how to say can be associated to so state operator correspondence. So if you add OI, acts on time t goes to infinity, acts on backing, and backing she corresponds to OI. So that's the state operator correspondence we want to impose in the in this example. So the following, the philosophy here. So if you just consider the some states on OI, states defined on this spatial circle on the not circle, spatial sphere, and but the theory is invariant under this time translation HC or dilatation here. Theory is invariant in this D, dilatation D. Okay? And therefore, if you go back to the far time past infinity, if you go to the far past infinity, this will just this sphere shrinks to the zero radius, and that would define some operator at the origin. Okay. So therefore, this the meaning is that if there is an operator, one can create a state. With a one-to-one correspondence, because that's a consequence of the scaling transformation. If the theory is invariant under the scaling transformation, and if you map to the cylinder, it's just time translation. Okay, unity time translation. And in theory, so since we impose this permission condition because we want to have the time translation unitary transformation. Okay, so you just go back and forth, go to future infinity and past infinity by unitary transformation. And then it's a Heisenberg picture, so that the operator depends on time. And if you go to infinity and acts on vacuum, that will create a state. Okay, so that's the state of correspondence. Okay. And this is very important concept and conformal. But this is only true in CFD. This is not true. Not true. This correspondence. There is no correspondence in general QFT. This is only true. Only for CFD. If you assume the general QFT this one, you immediately encounter some contradiction. So this is the very important concept, and I'm using this one. I will explain the correlation function and so on. Okay, let's stop here.